All right, here we go. So we're going to start off with here's the key functions that we've been working on the whole semester so far. And we kind of built this up. So we built up this idea. You know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment, right? That's what we've been working on. Okay, so we arrived here. We came up with these two functions. And so I want you to talk with the person next to you. For each of these two functions, what do we call it? Okay, talk to the person next to you. What do we call it? And then, maybe a slightly more important, what does it do? So what is the function of it, right? These are functions. What are their functions, right? What do they do? What do they achieve for us? Okay, so I'm going to start taking, what does this function do? What was the last part? The total amount you have? Nice and loud. The total amount you have between two given values of x. From A to x. It gives you the total amount accumulated. Is that right? Yeah.
Is it just the total amount that you have at x? So we have to add the A as our starting number, so then it's that plus.
Right. So I'm not quite sure what you said, but what I heard you say is like from A to x. Is that, I don't know, but maybe you didn't. But in any case, it's not just the accumulation from A to x. It's all the accumulation up to x, including everything before A, too. That's the f of A, right? That's all the accumulation up to A, and then what? This tracks accumulation bit by bit, then up to x. So then the total of that is all the accumulation from wherever negative infinity all the way up to x, or whatever the domain is. Okay, where is... Ni. Tell me what do we call this function? What's that? The second one, what do we call it? Exact accumulation at x. Almost. What else do we need in there? Yes, ma'am? Exact net accumulation. What do we mean by that? Can you say what does it do for us? What is exact net accumulation? Changing it, how it's changing every moment? That's the rate of change. Yes, sir. And what about from A to X? Okay. All right. So yeah, it's the net accumulation function. So it's tracking the amount of change starting from A till X. Change in what? Or the variation in what? It's tracking all the change in what from A to X? What quantity? So looking at these symbols here, quantity, which quantity? The quantity modeled by what function? F. It's the net accumulation in the quantity for F, right? Starting from A until X. Okay, so exact total accumulation gives the total amount of the quantity in question at any current value of X. Exact net accumulation gives how much F has varied starting from X equals A to the current value of X. So the quantity in question is modeled by the function F. And so A sub F will give the net accumulation, or how much F has varied from A to X. Super important. Okay, so if we wanted to write one of these, if we wanted to write, say, F or A sub F, what would we need? What would we need then to write for any quantity now? So not just height of a flag, right? We focused on height of the flag, but any quantity, temperature, distance, volume, what would we need?
The initial amount plus the integral of the rate of change.
Okay, yeah, so yes, exactly. We would need, what would we need? First and foremost, we would need the rate of change function. If we have the rate of change function, then we can write the exact net accumulation function, right? There's the form for it. There's the template. So if we have that rate of change function, we know what its exact net accumulation function. We can write it down. If you wanted exact total, what he said, you also would need the initial amount, right? You need the rate, and then you'd need that amount at A, the total accumulated amount at A. Okay, so we're going to talk about something different today. So I should say, so much of the semester we're going to be asking this question. We want to write an accumulation function for volume. What do we need? What are we going to need to do that? The rate of change of volume. I want to write an accumulation function for distance. What I'm going to need? The rate of change function, right? So for whatever quantity I want to write an accumulation function, whether it's total accumulation or net accumulation, if I have that rate of change function, I can write it down. That's all I need is the rate of change function. So the first kind of quantity or application we're going to do is area. Okay? So I want to write an area accumulation function. What am I going to need to write the area accumulation function? The rate of change of area. The rate of change of area. Because if I have the rate of change of area, I just put it in right there, and now I have a net accumulation for area function. Okay, does it make sense? Okay, so when we do this, when we talk about area, there's two issues. Of course, we just said we're going to need to determine the rate of change of area. That's going to be huge. And then later in class, we're going to have to investigate the impact on the function where the function values are negative. We'll talk about that at the end of class. Okay? So those are the two key things we'll need to do this. So we're going to spend most of the time talking about the rate of change of area. So where do we start? We start with constant rate of change, right? So we always start with constant rate of change. So is this blue region increasing at a constant rate? What about now?
Yes.
Is it increasing at a constant rate?
Yes.
Anyone say yes? Why do you say yes? But is the area increasing at a constant rate? Does anybody say yes? Who said yes? Why?
Because only one of the sides is changing, so it increase at constant rate as it moves across.
But isn't it kind of growing fast and then slow and then fast and then slow?
Because you're dragging it that way.
Right? Yes, ma'am. As opposed to what am I trying to trick you with? As opposed to what changing? Time, right? So there's two possibilities here. Is the area changing constantly with respect to time? No. Because of how I'm increasing the area. But even when I do this, is the area increasing at a constant rate with respect to the base of the rectangle or the x coordinate? Yes. You see that it is. Even if I jerk it or be smooth and then fast and then slow, it's still an increase, and that's what we're interested in. We're interested in the rate of change of that blue region with respect to the x coordinate or the width of the base of this region. Okay, so what is it? So we know that constant rate of change. What's our big important So what's our important principle about constant rate of change? What is it? Okay, with respect to x, and constant rate of change with respect to x, how do we model that? How do we understand that? dy equals mdx. And every time before we had the rate and we were finding variations in our dependent variable, right? Well, now we're kind of work backwards and we're going to figure out what is the rate of change. Okay, so that's now our goal is what is the rate of change of the area of this blue region? What is the rate of change? So let's look at some different possibilities. what happens here? So here we are, x equals 2. How much does the area change when I increase x, when I vary x by 1/2? So here I am at 2. I'm going to vary x by 1/2 to 2.5. How much did my area change? Anyone see? I'll do it again. When I varied the x value by 1/2, how much did the area increase? Someone said, you're thinking 1.5, you're correct. So what did I do? I varied x by 1/2. I got a resulting variation in area of, so this is like dA, now our dy is dA, right? Okay, what if I vary x by 2? So here I am at 3, say. I'm going to vary x by 2 from 3 to 5. How much did the area vary? 6, good. So when I vary by 2, my change in area is 6. And very quickly, we're seeing what the constant rate of change is. What if I vary the region by 1? If I vary x by 1, the area increases by 3. What's the rate of change? 3. See what I did? For any variation in the independent, we track the variation in the dependent, and then we're kind of working backwards to determine what m is. And it's very clear that it's 3. Okay, so when I start this animation up, where do you see the variation in the region, in the area? Where do you see the variation in the region? Where is it varying? Down here? Over here? Where is it varying? Right, well, okay, yes, but where? So in this region right here. So you're looking at that region. If I pause it, if I start it up again, where's it going to vary? Where's that region going to vary? On the right side, right? The right side is where we see the change of the variation, okay? So we said the rate of change was 3. What do you notice about over here on the right side? Yeah, y equals 3. See this right here? That height from the x-axis to the function is 3. And here we are at what? This is about 3.4. All right, how do we represent that height? How do we represent that height exactly? Here I am at x equals 3.4.
F of x equals 3.
Right now I'm paused at x equals 3.4. How do I represent that height? I know that he knows. Anybody else? Yes, sir. F of 3.4. So notice, the value of the function, or the distance from the x-axis, f of 3.4, is 3. And what do we say? 3 is what? Relative to this region. The rate of change of area. Huge point here. The rate of change of area is the value of the function at that x value. At least for constant rate of change. Okay, so at least for constant rate of change. So, what are the units on this rate of change? We did a little variation in x, and we got a variation in area. Say these are inches. Inches. What would the units be? So our area is in inches squared. Our variations in x are inches. So the rate of change would be inches squared per inch. Do they cancel out and become inches? No, because that's not rate of change anymore, right? Then that's just distance. We want to keep it as inches squared per inch because that represents rate of change, that for every variation in inches of x, we have this variation in inches squared. So what did we see? We saw that the rate of change of this blue region is 3, which is the value of the function at the right-hand side, or at the current value of x. So the rate of change of area is 3 inches squared per inch. But then we also saw that that's the value of the function. Now the value of the function is in inches. The rate of change is in inches squared per inch. So they have the same value but different units. So what will we do? We'll use the value of the function, and then knowing that it's rate of change of area, we'll adjust the units. So they have the same value. We're going to pull that value from the function to get the rate of change, but then we're going to switch the units. So same value, but then if we want it to be the rate of change, we have to have the inches squared per inch, or meter squared per meter, or centimeter squared per centimeter, or whatever. Okay, so what about when what is the rate of change of area when f is not constant? Right? So most functions have a changing value. So now how are we going to find the rate of change of area in a situation like this? Okay, here we go. That's the next step. So how did we do this before? So we kind of broke it down by constant rate of change, then we said, most rates of change are changing rates. So what did we do to move forward from there? Yeah. But that was the end result. So when we came to this point, we said most rates are changing rates. Yes, sir. Yeah, so we're going to break it up into intervals and look at constant rates over each interval to kind of maybe mimic that function. So here's that. So we're imagining generating area between the curve f and the x-axis. Okay, and what do we need? We need the rate of change. We need the rate of change of this area generated. So now, if you zoom in here, notice this has been modeled by lots of little constant values of the function. Okay, zoom in again so we can make it bigger. So we're zooming way in here. And this is what we're imagining. As that region is being generated between the curve and the x-axis, we're imagining split up into little intervals, and each little interval is we've estimated the function to be constant in that interval. It's kind of what we did. This was exactly what we did before. Now we're just doing it in the context of area. Okay. Okay, so here we are. Here's our x values, 90 through 96. Our y values of function f are around 1.5 to 1.7 in there, and you can see those values. So what I want you to do is, I'm going to break and do some more attendance. This is what you're going to answer. Is the value of x fixed or varying? What is its current value? And that's in the animation, right? In the animation. Is the value of x fixed or varying? And then looking at this particular snapshot, what's its current value? Is the value of delta x fixed or varying? What's its current value? Is the value of dx fixed or varying? What's its current value? And then finally, in the current interval, is the rate of change of area fixed or varying? And what is its current value? So I'm going to take some more attendance to answer these questions. Go. Hey, Paula if you're stuck, Paula can walk around and help you. Where's Zach? Is the value of x in the animation that you watched, was the value of x fixed or varying, Devin? In the animation. Yeah, x is a varying quantity. And what's its current value? Like 94. She said x was varying, and it's like 94. Okay, what about delta x? Fixed. And what's its value? Even in the animation, is delta x fixed? Yes. And its value? It's about 2. You should see that the value of delta x is about 2. Okay? From delta x is our intervals where we're going to keep things constant. So from like this is about 91.6 to about 93.6. So that's 2. Okay, Mackenzie, where's Mackenzie? dx in the animation, fixed or varying? Varying, and what's the current value in this, what we're showing here? So the same dx we had before, remember dx varied through intervals of delta x, as x varied through intervals of delta x, right? So what would dx, can you estimate what dx would be in this snapshot? Yeah, exactly, 0.5 or 0.4-ish. If you said 0.4, so it's from here. So here's the start of the delta x interval, and here's where we are. So yeah, so if you said 0.4 or 0.5, that's dx right there. And it's increasing. It starts at 0 in every interval, and it goes to what? 2, delta x. And then you get to the next interval, it starts over, 0 to 2, or delta x. Starts over, 0 to 2, delta x. Okay? All right. Somebody new. Where is Key? Tell me, Key. The current value in the current interval is the rate of change of area fixed or varying? In the current interval. Fixed. You agree? Yeah. So this is the whole point, that we, in these delta x intervals, we made steps, right? So that in a current interval, the value of the function would stay constant like this. And so therefore, the rate of change is staying constant. Again, leveraging constant rate of change in the varying situation, right? So we've got the situation where the y values are varying, but we're leveraging constant rate of change by making these steps. Okay, what is the current value of the rate of change of area? Wanna keep going? Key? What is the current value of the rate of change? In other words, what is rate of change of area at, where are we at, like 94? Here's a way to represent that. The rate of change of area at x equals 94 is about, we're going to estimate that to be, what's that? He wants 1.61. Agree? What did we say? The rate of change of area is the same as what? The value of the function, right? The value of the function. So this is we're getting that from f of 94. We're looking at the value of the function, or the y value, and we saw before that if, for the constant rate of change there, constant function, the rate of change is the value of the function. Now we know these units are different though, right? The value's the same, units different. Questions on these questions? Any questions on these questions? Yes?
I thought dx had to be like a different dummy variable.
You're thinking about t.
Yeah.
So that's when we do the accumulation function. So we're just talking about just rate of change on its own. When we build the accumulation function, then we need a dummy variable going from a to x. But we don't need that when we're just talking like we pause life and we're just talking about this. We're not accumulating anything. We're just analyzing this particular moment at 94. We haven't started talking about the accumulation function yet. We're just talking about the rate and what's happening at this moment. Other questions? There was another hand. Yes, please. Yeah, because so we get the number of the rate of change from the function, so the units on the function will be whatever this function is. So if this is, like miles, my cord's in the way. If this is miles, then function values will be in miles. But the rate of change is not in miles. It's in area per miles this way. So that would be like miles squared per mile. We talked about that earlier in class. Do you remember that? So the rate of change might be like in miles squared per mile, if all these numbers are miles. But then the function value is just itself miles. So the number is the same. We get the number of the rate of change from the function, but then we know its units are different. Yeah? So you imagine the animation, the area was being generated, right? So because we're generating area under these little constant steps, so if I was to increase x a little bit, the area would increase at a constant rate because the height is staying the same. We're leveraging the constant rate of change situation. So imagine the area under see this red bar right here? Imagine the region being generated under that red bar. Well, that area is going to increase at a constant rate because it's flat at the top. Is it better? Other questions? Okay, so then we imagine things getting really small, making delta x super, super small. And we're back to this situation. So imagine super small delta x's. All right, and in every delta x interval, it's a little teeny step, right? So here's two different situations along the way there. All right, so x is increasing, and the area is being generated, the region is being generated. So for each of these two, what's the current value of x? For each, what's the current rate of change of area? And remember, you're imagining that curve as a billion little tiny steps. Right? They're really small delta x values, and every delta x value has a constant value at the height of the function. Okay? So for each, what's the current rate of change of area? And then for each rate of change, give an estimate and express its value exactly in two ways. And then now that delta x is small, we're ready to write a function for the net accumulation of the generated area that I showed you, right? The area being swept out. At 2, he wants the rate of change as 1. Agree? At 2, the rate of change is about 2.5. Now we want to represent that. 2.5. What's two ways to represent that rate of change exactly? Some are saying f of 2. What do you think? Yep. And then what about another way? And then this is our estimate to that. So it's not exact something around 2.5, right? So 2.4 something. Okay, what about over here? Current value of x. 4.9 is about, okay? Rate of change. So we could say r of a of 4. We get that value from f of 4, and it is about? I'm going to say 3.7. How about that? If you said about 3.7, no, 3.5. Like 3. Wait. Yeah, about 3.7. 4.9. Sorry, 5. Better? Sorry, 4.9 or 5, right? We're talking about 4.9 or 5, not 4. Okay. And then the rate change is about 3.7. Okay, net accumulation area function for the generated area shown. So now I've got this function f. I'm sweeping out this area between f and the x-axis, and I want the net accumulation function. So what does that look like? A sub area of x. I'll give you that part. So I want to write the exact net accumulation for this. Yes, sir? So why did you chose 0 for A?
Because
Right, the region starts at 0, so the net accumulation starts from 0 to x of,
the R sub A of t.
and what is that? So we don't have an R sub A function, right? So we don't have an R sub A function. So what do we have?
The rate of change, so I guess F.
Is f the rate of change? Yeah, the value of the function is the rate of change, so f of t dt. So how many had that before he started me writing? How many? Not enough. Doesn't make sense, right? What do we say? This is the rate of change. We spent all class figuring out that the rate of change of area is the value of the function, which is this right face, this leading face of that region being generated. Okay? So there's our area accumulation function. Okay, so let's, question, sorry. Thank you, questions? Could I have said 0 to 2? No, because we want that, if you want 0 to 2, that's a particular area. To get that particular area, you need x to vary from 0 to 2. We've got to accumulate all the area up to there. So then you'd have 0 to 2, what? F of t dt. Because you need to vary from 0 to 2 to accumulate all that area. So you don't want to say 0 to 2 f of 2. If you do 0 to 2 f of 2, then you're going to get, here's f of 2. Then you're going to get all this if you do 0 to 2 f of 2. So that's why we need that t. That t is going to give us all the rates between 0 and 2 to get the blue. Another question over here. Yeah?
Where did you get the R sub A from?
We were, I just wrote it down as, we're trying to model the rate of change of this. So I called it that, right? So when we're looking at this blue area being generated, it has a rate of change. So I'm calling that function R sub A. And then where do we get that function from? It's the value of the function. The value of the function f is that rate of change. The height on the leading face on the right-hand side, whatever that height is, right? So when is the area being generated more quickly? Exhibit A or Exhibit B? Where's the rate of change greater? Over here in Exhibit A at 2 or at 4.9? 4.9, why? Because you have a taller leading face, right? That's going to, for the change in x, you're going to get more area here for the same change in x over here. Well, and that's according to how tall this is. That's the value of the function. Yeah? We're looking for the rate of change of area. We're looking for this, and this is what I'm going to call it. Where do I get that from? How am I going to get that rate of change of area? Where does it come from? So we spent all class discovering that that rate of change comes from the value of the function. Is that better? This is our goal. Our goal is rate of change of area. Well, what is the rate of change of area? It's the value of the function. So I can write it this way, knowing that that's my rate of change of area. Is it better? Other questions? Yes, please. Yeah, f of 2 is this y value. So if you integrate from 0, if you accumulate from 0 to 2, at f of 2, you're going to be accumulating at this rate. And you'll get that whole rectangle that I've shaded. We want the area just of the blue. So as x varies from 0 to 2, I need my rate to be according to this, which changes from 0 to 2. That's why I need f of t dt. T is going to take on all values from 0 to 2 and give me all these rates from 0 to 2 and give me the area, then accumulate the area of the blue region, not just accumulate at the value f of 2 the whole way. Is it better? Okay, good questions. Any others? Okay, so quickly, I got a little exercise for you here. So here I have a function f. And I've got this function, capital F is the integral from 1 to x of f of t dt. What is that function? What this capital F function is integrating from 1 to x of f of t dt. Do you recognize that function? What is it? Net accumulation. So it's net accumulation because it's an integral function. Is it exact? Yes, it's exact. It's integral. Of what? Of this area between f and the x-axis. And why do we know it's that? What? Because the rate of change is right there. That's the rate of change. The value of the integrand, that's the rate of change. If it's f of t, then it's giving us the rate of change of area. Okay, now, the other question we wanted to ask was, what is the implication of the fact, what happens when f is negative? See how for the green region, that's where f values were positive. And when the gray region is swept out, that's when f values are negative, and I'll show you that with an arrow. So this is a really big point. Don't tune out, pack up, and tune out. Just take a minute. What's the implication for the fact that sometimes f is negative? What's the implication for the net accumulation of area function? What's going to happen? So right now, what's happening to the net accumulation? Here it's increasing, but here it's decreasing, right? If the rate of change is negative, our accumulation will decrease. So area can't be negative, okay? Area is always positive. So all along we've been saying this is the net accumulation of area. It's really not, because of this case where the function can turn negative. Area is always positive. So we need a different name for this, and what we call this is signed area. Signed area has the possibility of being negative if your accumulation up to that point is the net amount is negative, meaning the amount of area below the x-axis is outweighing the area above. So instead of this being the exact net accumulation of area, it's this capital F function is the exact net accumulation of signed area. So at 1.5, is the value of the accumulation positive or negative? What about at 2? Is the signed area positive or negative? What about at 2.3? The net accumulation of area, signed area, positive or negative? Still positive. What about at 3? Then it's negative, right? Because all this accumulation down here has a negative contribution to the signed area, outweighing this. We'll pick it up here next time.